Hey everybody, Mr. Stewart here, and welcome to this screencast on the additive principle of counting. So the goals for your viewing today, firstly, I want you by the end of the video to be able to differentiate between various scenarios where you're choosing between what we call the multiplicative or the fundamental counting principle and the additive principle. In fact, in this particular video, what I've done is to be more efficient is I've chosen a problem that actually combines the two. And through that particular study, we can focus on the elements that differentiate them as well. And then we'll solve introductory problems involving this particular principle. So before we dig in a little bit further with our minds on math, just remember that the goal of video instruction really is for you to leverage time. Okay, so it allows you to view at your own pace and to deepen your learning at your own rate. Okay, so you might find that this video could come in handy later on when studying or reviewing to sort of ensure that you're able to master the concepts here. So remember from the previous lesson, our PowerPoint in class, the fundamental counting principle is stated as such. So in a nutshell, if something can happen in m ways and a second event in n ways, then the total number of ways that they happen together is m multiplied by n. And we can extend that into many more events. In fact, a very quick example here. Once I, for the first time, had a chance to study, you would call this combinatorics. We'll talk more about that in a future lesson. When I had a chance to study for the first time, every time I went in, and for instance, I'll use Subway as an example. Anytime you step up to the counter of a place where you have options to choose from in creating, in this case, a sub, my mind always goes there, and I'm thinking about different combinations. So I guess it's a bit of a occupational hazard. So very quickly, if we use Subway as an example, let's just say, for instance, we focus on our first choice, and they would also ask you, once you placed your order, what bread you wanted on. I can't recall the different types or all of them at this point in time, but for the sake of argument, why don't we just choose 2 or 3, okay? So our first choice is going to be the type of bread, okay? So B for bread, and we'll consider there could be whole wheat. I think there's honey oat. There's different ones. There's Italian as well, so I'm just going to put that in there. So let's just say we focus on those 3 as our favorites. Okay, so we have 3 choices of bread. Our second choice, of course, is going to relate to some toppings. And again, there's a variety of toppings, but let's just say choice number 2, your toppings. Let's say we're picky and we only really like a very few number of toppings. Okay, so let's say that you like things that are spicy, so we'll do some banana peppers, maybe some tomato, and we'll throw in some green peppers. Okay, so you'll notice that, and we're going to run out of room here very quickly, so it's important to plan this out properly, is that we have 3 choices beyond our choice of bread. Okay, so already we have 3 subs just based on that first choice of bread and our toppings. We'll also map that into the other types of bread. So depending on how you're feeling on any one day, you could make the same 3 choices. Okay. Last but not least, we're generally asked, what kind of seasons would we like, or, mustard, mayo, all the different sauces. So again, let's just say that we're kind of picky in that respect. And you're either a mustard or you're a mayonnaise type of person. Okay, so off of each of these choice of toppings, we are looking at mustard and mayo. So in essence, based on our first choice of bread, along with toppings and mustard or mayonnaise, it appears as though we have 6 different types of subs possible. Okay, If we went through the same process for the other two types of bread, you'd notice the same thing, that we would end up having all of these outcomes over here. So for this particular grouping here, another 6. And for the bottom group, we'd have another 6 possibilities. Okay, what I mean by grouping is I'm referencing this portion of the tree diagram. And this one here. So altogether, we're looking at 18 different submarine sandwiches. So another way to look at it too is according to the fundamental counting principle. Okay, so just flash back to the definition above. If you can make choices in m ways along with n ways of making a second choice, okay, because these events are occurring together. Okay, we're building a submarine sandwich here. What we can say is that the number of ways, so there are 3 here, and 2 here. So the number of ways would have to be the product of 3.
Meredith, your pizza's here.
3 and 2. So through that, we're looking at 18 subs. Okay. So the tree diagram is convenient in that sense in building understanding as to why the solution is 18. But at the end of the day, you might be actually able to circumvent the need for doing a tree diagram if you focus on fundamental counting principle and multiplying the number of choices that you have at each step in the process. So today, we need to focus on a different principle, okay, and that is the additive principle. So what I've done is I've chosen a problem that combines both. It plays off our knowledge of the fundamental multiplicative principle, and then it also adds in the additive, or the rule of sum. Okay? So as you move through the video, I would encourage you to pause where you need to and give yourself some time to jot notes and to think. And in fact, depending on your learning style, you might also find that it's beneficial to pause, not just to give yourself time to copy, but rather to give yourself time to think before you view the remainder of the video. Okay, so I would really challenge yourself to challenge your thinking in the moment. Okay, if you can do that and do it as we grow through the course, then you'll deepen your understanding and ability to work with the mathematics that much more. Okay, so here is our problem. So a company's website randomly generates confirmation codes, and we've done this, probably done this already when you go online and you are registering, say an account, or you're going to buy something. So the code consists of 3 symbols, okay, and those symbols are made up of letters and numbers. What I would ask us to do is to figure out how many codes can be generated if at least 1 letter is used in each. So recall what happened last time we worked on a problem that had the language or the words at least in them. So that's going to be important to us. So if we keep reading on, it's important that we do note that when we produce a 3-letter code, okay, that event, okay, or that action is independent or separate of, what happens when we're making a 2-letter code. And that action is independent of what happens when a 1-letter code is generated. So when you can identify events that are independent of each other, we say that they're mutually exclusive. Okay? They do not depend on each other. So if we were to consider what we've already learned, if we denote M or call M, right, the number of 3-letter codes, and the number of 2, and P, the number of 1-letter codes, then we can write the following statement. So the number of codes with at least 1 letter is M plus N plus P. Okay? So note the difference. With the fundamental principle, we were multiplying. With the additive principle, which is what we have here, for independent or mutually exclusive events or actions, we're going to use the additive principle, or sometimes called the rule of sum. So in terms of generating this, okay, the way we can set it up is to break it down into 3 parts. So we'll tackle each different type of code one at a time. Okay? So each particular type of code will receive the multiplicative principal, and then the additive principal will come in when we need to find the total number of codes. So for 3-letter codes, I want you to think about this here. If all we're concerned with is letters, that is from our alphabet, we're looking at 26 in each position of a 3-position or 3-symbol code. So what that means is using the multiplicative principle, okay, we would end up with 26 to the power of 3. And if we were to calculate that, it should give us about 17,576 codes. Okay. So using letters only in a 3-symbol code, we have just over 17,500 codes. Now your 2-letter codes, on the other hand, okay, we can only use 2 letters. So the last one must be a number between 0 and 9 inclusive. So we could look at it this way. We could say there are 26 letters, perhaps in the first 2 positions. Other codes could have them in the last 2. And then another set of codes could have their letters separated by a number. And there are 10 possible digits we could use for that number. So we'll backfill the rest of the codes. So what that means is that the number of codes that are considered letter symbol would be 26 squared times 10. And that's going to give us, let's see, I believe that's 6,760. And that same product is applied all the way through. For a grand total, or number of 2-letter codes of 20,280. Now, by like manner, we can apply the same thinking to the 1-letter code. And here's a great opportunity to pause and allow yourself to get caught up, but also allow yourself to move forward, okay, without the video. So with our 1-letter codes, again, only 1 letter possible, so it could occupy any one of these positions, and the remaining would be made up of numbers. So in each of these situations, we end up with 2,600 codes, where the letters and numbers happen to be in different orders. And according to that, we have 3 possibilities of 2,600 different codes for a total of 7,800. So altogether, okay, now that we've applied the multiplicative principle, we'll go ahead and utilize the additive principle, which is where the video began, and we'll simply find the sum of the different types of codes. 17,576. To that, we're going to add 20,280 plus 7,800. So in total, we should end up with 5,656 different codes. So again, 3-letter codes or 3-symbol codes made up of numbers and letters with at least 1 letter, just over 45,000. Now, at this point in time, you might be thinking that's certainly a lot of steps to get to that particular point in time. And that's good, and it's fine, because I think it does demonstrate a lot of great thinking and use of tools that we can use to communicate that thinking. Solution 2, we're going to use an indirect method of reasoning. Okay. So again, I would encourage you to pause your video and take a moment to think. If what we did was direct, that is, we had a direct approach to finding codes with at least 1 letter, what could be an alternate strategy to finding codes with at least 1 letter? Well, that strategy could be the following. Right? So why don't we think about subtracting the number of codes with no letters from the total? Right? So it's a 2-step process, really. We calculate 2 things, so I guess it's 3 steps, and then we would subtract, okay, as opposed to the several steps that we had before using a direct method. So let's start with the total number of codes. So that means that we have to consider how many possible symbols do we have for any one of the positions. So that means that there's no restrictions on what can be in those positions. So we could very well use letters and numbers. So we could say in the first position, we could have 26 letters or 10 numbers, which would give you 36 possibilities. Now that maps into the remaining possible choices too. So 36 by 36 by 36. So for our total number of codes, what we can do is we can multiply these together, and we have 36 to the third power, and 36 to the third power is going to give us 46,656 possible codes. Okay, so that's codes with no restrictions. So any number or any letter can occupy any of the positions. So to finish the process off, let's have a look at no letter codes. Okay, so no letter codes, so the 26 letters are not considered, which means we have 10 numbers to consider, 0 to 9 inclusive. So the product of that, so the third power of 10, or 1,000. So we have 1,000 possible no-letter codes. So therefore, the number of at least one-letter codes is going to be your total. So 46,656 minus 1,000 no-letter codes for a grand total of 45,656 codes. Okay. So that, in a nutshell, is how to differentiate between the two particular principles, and also how to use those principles together in a problem. So what you're going to see when we come back into the classroom, in MSIP, and in your own study time is a healthy list of questions, and you're going to find that there are some that are strictly focused on the fundamental principle. There will be some that are strictly additive, and you might find that there could be a couple that will blend the two principles together. Okay. So if you have any questions, please do jot them down. That's another great thing when you're viewing video, is to take notes, keep them at the margin, bring them up with your peers, bring them to me, or even if you need to resolve an issue right away, you're certainly welcome to message me over Remind or by email. Okay. We'll see you in class.